All right, today I will be working a few problems from chapter 10. So let's get started. In this first example, I'm going to do two things. First, I'm going to calculate the angular velocity for a wind turbine. And second, I'm going to find the angular speed of a CD. So we're going to approach this two different ways. Okay, so let's start with the first one. We were asked to find angular velocity, and recall that angular velocity is omega. Ooh, that is a bad omega. So we were also asked to find angular velocity in radians per second. And that should say radians per second, not radians per second squared. I apologize for that. So that should not be there. We know a couple of things. So let's go ahead and write them down. We know, number one, that 2 pi radian is equal to 1 revolution. The second thing we know is that 1 minute equals 60 seconds. Okay, these are both going to be important because we were given revolutions per minute, but we were asked to find our velocity in radians per second. So we're going to have to start with a conversion. We're going to need to convert 17 RPM into radians per second. So let's do that. So there's revolutions per 1 minute. Okay, let's use this piece of information first. So 1 revolution is equal to 2 pi radian. And then finally, we have 1 minute on the bottom. So let's write 1 minute is equal to 60 seconds. And when you do this math, you will find that it equals 1.78 radians per second. Now here, I actually need to point something out. Notice in the problem that it said our wind turbine was rotating clockwise. Recall from the concept video that if we have clockwise rotation, we are moving in the negative direction. So this would actually be a negative 17.0, and this would actually be negative 1.78 radians per second. So this is the only thing we have to do for part A. That's part A. Okay, now part B. And I switched colors. In this problem, we have been given degrees. And again, if you remember back to the concept video, we are going to want to use radians in our calculations. So the first thing we should do is convert degrees to radians. Well, 2 pi radian is equal to 360 degrees. So if we convert that, it's 106 degrees. And then we put 2 pi radian on top. And we find 1.85 radian. Knowing this piece of information, we now have all that we need to plug into our formula. So omega is equal to the change in theta divided by the change in time. And this is our change in theta. That's how far that CD has rotated. So we're going to put 1.85 radians divided by 0.0860 seconds. And we will find that in this case, the angular speed of the CD is 21.5 radians per second. Okay, so those weren't too bad. We were mostly just practicing unit conversions here. So let me erase this. And let's look at the next one. Here we have another baseball problem. I told y'all these are very popular with this textbook, and I like baseball too, so I choose them. We will be finding the angular acceleration of the ball this time, and then we're going to be finding out how many revolutions the ball makes before it is caught. Okay, so take a look at your formula chart and see if you can locate something, an equation, that would be appropriate to use here in part A. Okay, I hope that you chose this. Oops, that's alpha t. Okay. Since we were asked to find the angular acceleration, we should rearrange this equation so that we are actually solving for the acceleration. So when I do that, I'll find that my angular acceleration is equal to omega minus omega naught over t. Okay. Now, why did I choose this one? Well, I looked at the information I was given in the problem, and I have an initial angular speed, I have a time, and I have the angular speed afterwards. So I have all of the variables I need to just plug in and solve for acceleration. So this part's going to be very simple. Let's plug everything in. We have 34.2 radians per second minus 36.0 radians per second divided by 0.595 seconds. We'll do this math, and you're going to get a negative value here because when you subtract 34.2 minus 36, you're going to get a negative value. So this would be negative 3.03 radians per second and squared. This is squared because it's acceleration. Okay, that's part A. Pretty simple. Now let's do part B. Okay, so again, let's take a look at that equation chart and see which equation will be the most appropriate to use here, because we want to know how many revolutions the ball makes before it is caught. In other words, we want to know the change in theta. So take a moment to choose an equation. Okay, and here I hope you chose this equation. If you didn't, that's okay, but this is going to be the best equation to use for this. Now, it doesn't have the change in theta here, but we know that a change in theta is just equal to whatever the final theta is minus the initial theta. We have initial, we have final, so we can find this, and let's go ahead and rearrange, so we're doing that. Final theta minus initial theta equals omega naught times t plus 1/2 alpha t squared. Okay. We can now plug in the information that we have. So we're going to be, I'm sorry, these are bad again. Equals, okay, this is 36.0. Our time is 0.595 plus 1/2. Now we just solved for the acceleration, so it's right there, negative 3.03. And finally, we have time again, so 0.95 or 0.595. And when we calculate this, we will find that our change in theta is 20.9 radians. Now, we were not asked for radians. We want to know how many revolutions the ball makes before being caught. So once you get to this point, we need to convert radians to revolutions, and that's pretty simple. So let's plug in what we know. 2 pi radian is equal to 1 revolution. And we will find that the ball made 3.33 revolutions. Okay, so that is your final answer here. Okay, let's look at a third problem. Okay. So here we're looking at the tires on a car, and we're going to find both the angular and the linear speed at the tops of the tires. Okay, if you are reading this question, I hope you've already noticed a couple of things. Number one, we're given centimeters. Number two, we're given miles per hour. We can't use centimeters in any of these equations, and we can't use miles per hour. So let's just go ahead and convert those before moving on any further. Okay, the first one's easy. 31 centimeters is 0.31 meters. Let's also convert 65 miles per hour. 65 miles per 1 hour. And I just looked up how to convert from miles to meters. So 1 mile is 1609.34 meters. But don't worry, if you needed to do that on an actual test, I would have provided you that conversion. I do not expect you to know it. Okay, 1 hour. So let's put an hour on the top, 3,600 seconds on the bottom. And you'll find that it is 29.06 meters per second. Okay. Now, if we are looking for the angular speed, that's omega, and omega is v over r. Okay, so let's plug in what we know. We've already done our conversion, so this is going to be simple. Okay, and then we converted that. So we'll find that the angular speed of the tires is 94 radians per second, or you can just put 94 seconds to the -1. That's fine too. It doesn't matter. Okay, that's part A. Now let's find the linear speed of the tops of the tires. So let's find part B. Okay, this one is actually extremely easy. Maybe you've already figured it out. Maybe you haven't. Since we are using linear speed, we're going to go back to looking at miles per hour. We didn't need meters per second for this part. We just needed it for that angular speed part. So the tops of the tire have a speed of 2 times the velocity. Okay, that means 2 times v is 2 times 65 miles per hour. So that would be 130 miles per hour. Or if you wanted to, I guess you could have done this in meters per second, and you would have just taken 29.06, multiplied it by 2, and got an answer there. So honestly, it doesn't really matter. It didn't specify which units it wanted it in. Again, no worries. If you see that on a test or quiz, I will specify. Okay. And moving right along, we are going to look at this grindstone, which is sharpening an axe. Okay, so here we've been given the linear speed relative to the axe. So we have that. And we know the stone's kinetic energy, the rotational kinetic energy. So we want to find the moment of inertia. Again, take a look at your equation sheet. And I hope that you can see that the equation that relates kinetic energy to the moment of inertia looks like this. We have the linear speed, so we can find the angular speed here. And then from there, we'll have all the information we need in order to just plug everything in to this formula. Okay, so we do not currently have angular speed. We only have linear speed. So let's calculate the linear speed. There's omega is v over r. Okay, well, we have that. We know it's 1.50 meters per second. And we know our radius, it's 0.610 meters. That looks like a 6, it's a 10. Okay, so our omega here is 2.46 radians per second. Now that we have omega, let's just plug everything in and solve for I. Actually, I'm going to go ahead and rearrange this so that it's even easier. So I is equal to 2 multiplied by k divided by omega squared. Let's plug in our values. That's going to be 2 multiplied by 13 joules divided by omega squared, which is 2.46, and that's radians per second, and that's squared. So now we can see that I is equal to, I'm going to write that, well, I'm going to try to fit it right here. 4.30 joules seconds squared. Or if you did not use joules, you could have just said that this was 4.30 kilograms meters squared. Either is fine, but I'm going to stick with joules. No need to do any extra work at the end of this. Okay, so let's do part B now. I'm going to switch colors again. Okay, part B. If we double the linear speed, what will the corresponding kinetic energy be? All right, well, if we double this linear speed, what's going to happen to the angular speed? Hopefully, you can see that it will also double. So if linear speed doubles, angular speed is going to double as well. And we will have 4.92 radians per second. Let's plug in what we know. K equals 1/2. We know the moment of inertia because we just calculated it. And that's joules seconds squared. And then we need our new omega value, which is 4.92 radians per second. Let's square it. So the kinetic energy here would be 52 joules. And that's it. Okay. Moving on again. And we're doing something else with this problem. Okay. If the grindstone here is a uniform disk, what will its mass be? Okay. Take a look at that equation sheet again. For a uniform disk, we know that I is equal to 1/2 mr squared. Well, we know what I is. We calculated it in the previous problem. And we know what the radius is. There we go. So we can solve for m. This is going to be very straightforward. Let's rearrange and we get m equals 2I over r squared. Plug it all in 2 times. And that inertia was 4.30. Oh, what am I doing? Joules seconds squared. And that is divided by 0.610 meters. That's my radius. And we're going to square that. So you should find that your mass is equal to 23.1 kilograms. So I guess here it would have made more sense to use the kilogram meters squared instead of joules so that you could see how I actually got this unit. Okay, so here is your answer to this problem. That was extremely easy. Okay, and we're going to work one more problem. Okay, so in this problem, we're looking at a basketball, which is pretty much just a hollow sphere. And we want to know what the translational kinetic energy is, the rotational kinetic energy, and the total kinetic energy of the ball. So if we have our basketball, I don't know how to draw this. What does this look like? Kind of looks like a basketball. That's fine. Okay, so we see that its radius, oh, they gave us centimeters again. So let's just go ahead and convert that. We know we're going to have to. There's no sense in avoiding it. So the radius here is 0.121 meters. And then we also know that it is moving with a linear speed of 1.33 meters per second. Okay, I'm going to go back to using this orange color. Okay, so let's do the first part. Part A, we need to find the translational kinetic energy. And this is going to be the easiest part. Translational kinetic energy means we're just going to use K equals 1/2 mv squared. So the very straightforward kinetic energy formula. It's 1/2 mass, which is 0.650 kilograms, times a velocity. And we see that right here, 1.3 0.33 meters per second squared. So my translational kinetic energy, and I guess I should label that with a T, my KT, is equal to 0.575 joules. Okay, that's part A. For part B, go to blue now. We need the rotational kinetic energy. Okay. Looking at your equation sheet, and you can always pause this if you need more time to search. So the rotational kinetic energy can be found through the following formula. K equals 1/2 times the inertia times the angular speed squared. Okay, well, we don't have the inertia and we don't have the angular speed. So we need two different things here because we only know the linear speed. If we do not have the information we need to find it, we can just substitute the appropriate formulas in. So it tells us this is basically a hollow sphere. For a hollow sphere, I is equal to 2/3 mass radius squared. And we also know that the angular speed is equal to the linear speed divided by r. So let's go ahead and plug all of that in. So we have 1/2, and we're going to have 2/3 mr squared v over r squared. A lot of things are going to cancel out. So let's go ahead and do that. Well, not a lot, but a few things are going to cancel out, and I'll switch back. Okay, so the 2's cancel. My r squared is going to cancel. And the only things that are left here are going to be k is equal to 1/3 mass velocity squared. Well, we have all of that information. We know the mass. We know what that velocity is. So let's just plug in what we know. Okay, so that's 1/3, 0.650, and 1.33 squared. So my kinetic energy, my rotational kinetic energy, is 0.383 joules. To find the total kinetic energy, we're just going to add these two together. So part C, we're just adding the rotational and translational energies together. So here's part C. Let's take 0.575 joules plus 0.383 joules. And that equals 0.958 joules. Okay, so there's our total kinetic energy of this basketball. So that's going to be it for working problems. If you would like more examples, you may find them in the book. And I have given you a study guide if you would like to do any of those problems to prepare for your quiz. Make sure you have that formula sheet. Write all of these down. There's a lot of formulas in this unit, but most of them aren't new. The only thing that's new is we now have angular components instead of just linear components. So if you have any questions, please post it in the discussion. And if it doesn't get answered there, please email me. Y'all have a great day.